Ever wonder how plants manage to satisfy their thirst and enjoy the sunlight? Well, it's a fascinating tale that begins with the roots, which act like straws sipping water from the soil. The water not only gives the plant structure, but also acts as a carrier for nutrients. When a plant performs photosynthesis, it opens tiny doors on its leaves known as stomata, welcoming carbon dioxide from the air. But there's a catch. While these doors are open, water vapor slips out, a process we call transpiration. Now, picture this. The soil is a bit like a sponge, partially saturated with water. This moisture can either enter the plant roots, meander to other soil parts, or trickle down to the water table, a zone completely saturated with water. Here, soil moisture transforms into groundwater. The top layer of soil exposed to the sun and wind may even turn its moisture into vapor, joining the atmosphere. This transformation of liquid water into vapor through transpiration from plants and evaporation from the soil is what we call together evapotranspiration. Evapotranspiration is one of the highest flows of water on Earth. The hydrological model known as CWAT-M, or the Community Water Model, simulates evapotranspiration. It considers various land types like forests, grasslands, and different types of agriculture. Each of these uses water differently, influenced by factors like weather, time of the year, vegetation type, and of course the amount of water in the soil. Imagine a plant with a never-ending water supply. The amount of water it would use is what we call potential evapotranspiration. We calculate this by comparing this with the water evapotranspired by a standard grass field. The water transpired by the standard grass field is called reference evapotranspiration. A widely accepted method to do this is the Penman-Monteith equation, which factors in temperature, solar radiation, wind, and humidity. The water used by a specific land type compared to the standard grass field is known as the crop coefficient. So, if a land type has a crop coefficient of 1.5, it uses 1.5 times more water than the standard grass field. In the CWAT-M model, crop coefficients for each land type are key inputs. The crop coefficient inputs provided with CWAT-M are different for each land type and vary spatially and temporally in 10-day time steps for a standard year. To include specific agricultural plants or crops in the model, the CWAT-M needs the following pieces of information. When and where the crop is planted, the total growing period divided into 4 growth stages, and the crop coefficient for each growth stage. These data are available from the Food and Agricultural Organization and several regional and crop-specific studies. Studies sometimes provide 3, 4, or varying crop coefficients. For CWAT-M, this must be adapted into 4 crop coefficients for 4 growth stages. So the next time you marvel at a lush green field or a towering tree, remember the intricate dance of water and sunlight that sustains them. CWAT-M can be used to understand the spatiotemporal pattern of evapotranspiration and can be used to investigate the influence of different land and management scenarios on the water cycle and availability for nature and humans, including under future climate and socioeconomic projections.